Hello, everybody. So today I would be going over how to compute a unit binomial vector and also torsion. So I'm going to first start off with a unit binomial vector. Um, there are two formulas for the unit binomial vector. It's either b is equal to the tangential unit vector cross with n all over. Oh, sorry. Yeah, that's it. Yeah, these two. So the tangential times the normal, and then the other formula for it is v cross with a unit vector. Um, so this whole thing is a unit vector because it's being divided by the magnitude of it. V cross a. So we understand that v is the second is the derivative, and a is the double derivative. They stand for acceleration and velocity. So the way I can think about it is like, let's say this path, right? Which is this the path we're doing. So if we have this certain path, right, that means the tangential vector, let's say right here, is going to be like this. And that is saying that the normal vector, it's going to be like this. A normal vector is going to come out of that because we're doing the cross product. And because of that, and then that vector, that unit vector that's going to come out of it is considered the binomial vector. Okay, so because earlier I said we were going to do torsion, I'm going to stick with this formula because we don't have the tangential unit vector and we don't have the normal. Um, so remember, tangential unit vector is just the derivative of r prime divided by itself. So that's a unit vector and times the normal, and then the normal can be calculated with the derivative of the tangential over all over the tangential magnitude. So I'm just gonna use this formula right here because we're gonna use all those derivatives. So let's write it. So r t should be equal to, if we do component by component, so 4t 25t to the fourth 3. And now the double derivative, we should have 4, we should have 100, then should have 0. And then torsion, I'm going to show the formula for torsion, but torsion requires a triple, um, not a triple, third prime, 3 prime. So 1, 2, 3, t, this is 0, this is 300, t squared, 0. Okay, so now let's do the cross product of v cross a. So this is v, this is a. So let's set it up. So we have I, J, K. So V will go up top. So we'll have 4t 25t to the fourth divided by and then 3. And then the double prime, and then this double prime is 4 100t to the third, and then 0. Okay, so let's compute this cross product. So this times this will be 0, and then this times this will be negative 300 t to the third is the I component minus, so So if we cover up j, we have 4t times 0, which is 0, and then negative, and this is going to be 4 times 3, it's going to be a negative 4 times 3. It will become positive, so this will be 12j. And then plus, and then we have 400 t to the fourth minus, and then we have 100 t to the fourth. That's k. So let's write it down in better form that I prefer. So negative 300t to the third, and then 12, and then we can simplify this, so this will just be 300t to the fourth. Okay, so that's good. So now we have this. So now we need to find the magnitude of it. So let me go down a little bit. And if I do the V cross A, the magnitude of it, so 300 squared t to the 6 plus 144 plus 300 squared t to the 8th. So let's simplify this, and then so maybe what we can do, it's not really much we can do. I mean, we can pull out 3, but I mean, honestly, this is the best way. Yeah, we can leave it like this. This should be fine. And so, because the formula is this over V cross A, we can literally just put this all over here, and it's understood that all of this goes to each component. Square root 300 squared t to the 6 plus 144 plus 300 squared t to the 8th. Okay, so and this is considered our unit vector, our binormal unit vector. Okay, so that's the answer. So now I can move to torsion. So torsion, it should have this general equation. So this is tau, right? Torsion is it's denoted as tau. So we have, I'm gonna denote it as with A's and V's. So V cross A dotted with R prime, R triple prime, and then, well, technically the triple derivative of position is jolt. So maybe we can just denote it as J for jolt. And then all being divided by the magnitude of V cross A squared. So the good thing is that we already have what V cross A is, which is, and then we already have the magnitude of that. That's why I started with binomial first. So if we grab our binomial vector, we can say that this is 300 t to the third 12, 300 t to the fourth, and then if you see right here, the magnitude, right, is being squared. So all of these up top, so all of this in the denominator, that square root can actually go away. We can say 300 squared t to the 8th plus 300 squared t to the 6th plus 144. And then remember, we're still dotting it with the triple derivative. So what's the triple derivative? It's right here. So maybe we can move these. I'm not sure how to do that. Yeah, I'll just write it. So 0, 300 t squared 0. Okay, so because you're dotting it, a torsion is actually a scalar because you're dotting two vectors. So let's do it. So this component will go away because you're multiplying by 0. The j component will actually not go away, and it will just be 12. So 12 times 300 is equal to 3,600 t squared, and then the k component will go away, and then this is all over 300 squared t to the 8th plus 300 square t to the 6th plus 144. And this is torsion. So the binormal vector is helping us find the torsion of it. So if I go back to the diagram right here, so we're pretty much utilizing the binormal vector, and we're doing the scalar of it. So it's how much this binomial vector is turning in a way. How much torsion does it have in a certain direction? So we're using this binomial vector to find out the torsion of it. So that's it for